Our next section, we're moving on to one-to-one functions and implied domain. Let's go to the first slide, match up with our notes. Here we are talking about one-to-one functions. We like to use this notation as a shortcut to writing one-to-one, 1:1, or 1 and the word 2, TO, is the symbol we use for one-to-one functions. This says each x value maps onto a unique y value. So the test for a one-to-one function must pass two tests. The first test, which we've already been introduced to, is to see if the function, so it must pass the vertical line test. And the second test, if it passes the first test, then you try the second test and we apply what's called the horizontal line test. The horizontal line test must also only cut the graph once. Okay, only once. So let's have a look at these four examples here. So here I've got a straight line. We can see that it will pass the vertical line test. Doesn't matter where I draw the vertical line. At the most it cuts the graph at one point. But if I not change colours, if I do a horizontal line test, a bit hard to make it look horizontal, but if I draw a series of horizontal lines, it's only cutting our blue graph here, a straight line, our linear graph, only once. So we'd say this is a one-to-one function. I'll put a little ones like that. Okay, so if we go to the second example here, we've got an upside down parabola. Okay, we can see that a parabola passed the vertical line test, series of vertical lines. Doesn't matter where I draw the vertical line, it doesn't cut the graph more than once, so it is a function. So it's something to one. But when I draw the horizontal line test, it cuts the parabola, you can see here, it cuts it at more than one spot, cuts it at twice. There is a case where up here it doesn't cut the parabola at all, and there is the case here, it's hard for me to draw this exactly, but when it's what we call a tangent, just touches the turning point there, only cuts it at once. But because there are spots where it cuts it more than once, we say this is not a one-to-one function. This would be a many-to-one. Many x values produce the same y value. So we say this is not a one-to-one, this was a one-to-one, which is basically what we're trying to look for here. So here we've got a parabola here again, so we can see that it passes the vertical line test. But if I draw a horizontal line, you can see it cuts the graph at more than one position. There, that horizontal line cuts it twice, so therefore it's not a one-to-one. It's another example of a many-to-one. And here I've got a circle. We could look at this question two ways. As a complete circle, blue and the red combined together. It's certainly not going to pass the vertical line test because it's not a function. Well, it's not very vertical, but that is. Okay, because it cuts the graph, so it's not a function as a circle. But if I just considered the positive square root, which is the top part of the circle, the top semicircle, we can see it is a function because it only cuts the graph at one point, which is there and there. Or if I just looked at the red graph separately, the bottom half of the circle or the semicircle, we can see that it is a function. But we can see here by drawing a horizontal line that the blue is not a one-to-one function because the horizontal line cuts it more than twice, and the same argument would be for the red semicircle or the whole circle as a whole. So we say this is not one-to-one. Let's move on to the next slide. This next part of the slide talks about implied domains. Quite often we're given a rule, but it doesn't actually tell us what x values to use. So we need to use what we call the maximal domain. That is, we use as most x values as we can. So what we're looking for is where we can't use, what numbers we can't put into the rule. So if we look down at example A, we've got f of x equals 2x squared. So we know this is a parabola. Recognizing the rule certainly helps you to have an idea. So the graph of 2x squared looks something like this. It's a upright parabola going through the origin. So there's the graph of f of x equals 2x squared, looks like that. Is there any x value I can't put into this rule? There's no restrictions. I can put any number where x is, and I can work out the y value. So we say here the implied domain, it's not stated for me, what x values can I put into this? The implied domain, I use the maximum amount of values I can. In this case here means I can use all real numbers. So we say that implied domain is R. When we look at B, we've got g of x equals root x. Now we've already studied this, so we know that the graph of root x looks something like this, starts at the origin and goes upwards and outwards with a bend that way. So we've also, when we looked at the square root graphs, we recognised that we can't put a negative number into the square root. So the implied domain in this question is I can put 0 in because I can have the square root of 0 and anything bigger than 0. So in the interval notation we say that's 0 to infinity with a square bracket at 0 and a round bracket at infinity. That's the implied domain. That's the maximal domain. I can put any one of those numbers into the rule g of x equals root x. Okay, if we look at the third example here, where we've got h of x equals 1 on x, hopefully we recognise this as the hyperbola. Now you might remember the hyperbola has two branches. One branch looks like that, and the other branch looks like this, for a bit of curve. But we might remember that on this graph there was a vertical asymptote and a horizontal asymptote. So knowing our graph types and recognising the rule that produces it, so 1 on x, yes, I know it's a hyperbola, so it helps me now talk about the domain. What x values can I use? Well, this says I can go out to negative infinity and no problems, and go out to positive infinity, no problems. The only problem we have here is when x equals 0, the function's not defined. The reason being is I'd be dividing by 0 if I put 0 into this rule, and in mathematics that has no meaning, it's undefined. So we'd say the implied domain here is R, excluding, curly bracket, 0. All right, so the two functions that Year 11 method students we've got to be very careful of is the square root function, and we need to be careful of hyperbolas when we have fractions. We can't have 0 on the bottom. So let's extend this a little bit. Don't know what I was doing there. Okay, if I now made the rule negative x, the domain here would be actually negative infinity up to 0. The reason being, for example, if I put negative 3 in this rule, it will become square root of negative 3, which makes that positive 3 under the square root, so that's okay. But if I put 4 into the rule, for instance, it would become square root of negative 4, which I can't do. So extending that, sometimes we see the rule looks something like this. 3 take to x. Now we've got to remember when we see a rule like this, we can't have a negative number under the square root, so we actually need to solve this problem first. We say 3 take x has to be greater than or equal to 0. That can equal 0 or has to be a positive number. That's greater than or equal to 0. If I solve this inequality, I take 3 from both sides, I get negative x is greater than or equal to negative 3, but I need to get rid of this negative, so I divide both sides by negative 1. And you might remember when we divide by negative 1, we need to change the inequality around. Negative 3 divided by negative 1 makes positive 3. So the answer here is x is less than or equal to 3 is our domain, so we'd be writing that as negative infinity to 3, but it says here equal to, because 3, putting 3 in this rule makes 0. If I put 2 in this rule, 3 take 2, square root of 1 is fine. If I put 0 here, it'd be square root of 3 take 0, square root of 3. Okay, but if I put a number bigger than 3 in, like 4, 3 take 4 makes negative 1. So this graph, this square root graph actually starts here at x equals 3 and actually goes that way because we've actually got a reflection in the y-axis. We don't study those in year 11, it's a year 12 methods thing. Alright, the same goes down here when we talk about 1 on x, so we have rules that we should know about is 1 on x, and the similar one that we've already studied is the truncus, which is 1 on x squared. Can't put 0 on the bottom of a fraction, so we're always looking for something. How would we make 0? So if I was looking at the let's have a look at, if I had the rule 1 on x take 1, we need to think about what number would make 0 on the bottom. So this, what we need to do is solve this equation. When does x take 1 equals 0? Oh, that's when x equals 1. So the domain of this question would be R excluding 1. If we have a truncus, like here, we're looking also, we can't have 0 on the bottom, so it doesn't matter what the rule is. So if I had something like 1 on x plus 2 all squared, now we know that's a truncus that's been translated 2 units to the right, but we just have to work out when x plus 2 is equal to 0. Take 2 from both sides, so we get x is equal to negative 2. So if I come over here, I'd write the domain here as R excluding negative 2. Okay, proceed to the next slide. Alright, here we've got 2 examples. I'm just going to draw a line down between them so I can separate the 2 examples. It says for each of the following, state the implied domain. So we're going to and sketch the graph. Okay, we've already studied these types of graph. Here's our square root graph. A good way to consider this graph is this can be written as the square root of 2 bracket x take 5 over 2. It's not very well written, but we can see really it's a translation of 5 on 2 units, not 5 units. The translations inside the function, you actually always got to have it as just x, so you have to factorize it. So I've taken 2 out as a common factor there. All right, the implied domain here is what aren't we allowed to have under a square root? We're not allowed to have negative numbers, so this rule under the square root is 2x take 5 has to be greater than or equal to 0. So if we solve this equation, we get 2x, add 5 to both sides, so it becomes 2x is greater than 5, and divides both sides by 2 because it's a positive number. We don't change inequality, and we get x must be greater than 5 on 2. Alright, this is a square root graph. There's no translation up or down, so we can probably proceed to draw this graph pretty quickly. So x and y. The implied domain is x has got to be greater than or equal to 5 on 2. It's not moved up or down, so this is a question where we've got a translation of 5 on 2 units on the to the right, so that value there is 5 on 2. It's actually the coordinate 5 on 2, 0, the y value is 0, and it's a square root graph, so it's going up and out like this, and that would be the graph. If you go to when we go to the next slide, you'll see a better version of this graph. So the implied domain was x has to be greater than 5 on 2, or we can write that as 5 on 2, comma, infinity, anything bigger than 5 on 2. And so I've answered the question, state the implied domain, that's the implied domain, and sketch the graph. All right, part B. Here we should be recognising this as a hyperbola. It's 1 on x to the power 1. Doesn't matter what the numbers are around it. We also could do what we did in the previous one, consider this as 1 on 2 bracket x take 5 on 2. Alright, so we can say there's a translation of 5 on 2 units. There's actually a dilation factor of a half, 1 on 2, from the x-axis. Let's do the domain part first, the implied domain. What aren't we allowed to do with a fraction? We can't have 0 on the bottom, so therefore we've got to solve this equation that whatever's on the bottom, 2x take 5, we want to know when it's going to equal to 0 because that's the value we're not allowed to use. So it's very similar to what we did over here on the left. So we get 2x equals 5 by adding 5 to both sides. Divide both sides by 2 and you get 5 on 2. So therefore the domain, that is a D, the domain, DOM is good enough, is going to be R, all values are okay, except, because this is a hyperbola, except one value, in this case it's the value where it's 5 on 2. Like I said, on the next slide we'll see a much nicer version of this. Right, so now I should better sketch the hyperbola here. So set my axes and label x and y. Never forget to do that. Okay, we've got a vertical asymptote. It's been shifted 5 on 2 units to the right. That's the value we're not allowed to use in this rule. The implied domain helps us doing that. This is a vertical line, so we need to label with the equation x equals 5 on 2. There is a horizontal asymptote because it's a hyperbola. I'm just going to change the color here so we can see it. It hasn't been moved up or down this graph, so the horizontal asymptote is along the x-axis. That's why I changed color, just so we can see it, and that's got the equation y equals 0. It's a hyperbola, there's been no reflection, whatever, so my hyperbola is going to come down like this and come across like this. So we can see we do have a y-intercept, so I need to put 0 where x in the rule, and when I put 0 where x in the rule, when x equals 0, we're going to get y is equal to 1 on negative 5, which is negative 1 on 5. We don't leave the negative on the bottom of a fraction. So that coordinate there is 0, negative 1/5, or negative 0.2. And that's the graph that we need to draw for this. So if we go to the next slide, we can see what they should look like, nice and neat. So there's our square root graph on the left. Here we get the implied domain of x is greater than or equal to 5 on 2 by solving that equation, which we did on the previous page. And so essentially it's a square root graph that's been translated 5 on 2 units to the right. It's actually, there is a dilation factor going on here, but when we have the dilation factor inside the square root, that's year 12 work, not year 11. And over here we can see g of x is equal to this hyperbola. We solve the equation. We want to know when 2 of x take 5 is not equal to 0, and that was when x equals 5 on 2. So our implied domain was r excluding 5 on 2. And you can see we've got our vertical asymptote, we've got the horizontal asymptote there. It's hard to pick up, but it's actually there. They're both labelled, and the y-intercept has been calculated for us.